This is the third video in the series of Chapter 2. I should be able to finish what I wanted to talk about in this video, but there's also something else I wanted to show you that I might be able to fit in here now. So we'll see how that goes. So we finished the second video in this series on a little bit of calculus. Basically taking an average and making it more and more instantaneous by decreasing the interval that we were averaging over. And I skipped a whole lot of calculus here. You're going to learn all about this in calculus, but we're going to need the rule for some problems in physics. So I'm just going to show you the rule. You can memorize it. I actually, what is this? The power rule? My calculus, you take it a long time ago. You don't remember all the names, but I remember the rules anyway. I think this is the power rule. Someone can correct me in class if I'm wrong. Just basically for now, memorize it. When you get to it in calculus, you'd be like, I already learned that, haha. But then you learn how or why it works, and I'm sure they'll prove what's going on. Anyway, so that's instantaneous velocity. Just let's review a little bit. Back here, we said that velocity is how fast your position is changing. Right? Let's take it up a notch. What if we ask, how fast is our velocity changing? How fast are we speeding up, or how fast are we slowing down? And we have a name for that too. And it's called, oh, I'm writing with the mouse right now. Let me bring my pen over. Okay. There we go. It's a little easier. It's called well, maybe it's not easier. Acceleration. How fast is my velocity changing? Doink. And symbolically, we could write this as, well, we can, just like we did an average acceleration and an instantaneous acceleration, just like we did an average velocity back here, and then an instantaneous velocity, same rules apply. We can do an average acceleration and an instantaneous acceleration. Average acceleration is going to be change in velocity divided by the change in time. And hopefully you're picturing what a graph would look like. On the y-axis of our graph, we will have velocity. Well, actually, hey, let's bring this over. Remember this thing? Now, let's add a little check box here. Ding! Oh, look at that. Our y-axis is now velocity, and our x-axis is still time. And by the way, these two graphs are linked, and that's kind of what I was hoping to discuss additionally in this video. And as you're going to see pretty soon, we can check this too. Ding! And we get acceleration on the y-axis and time on the t-axis. We're going to need to understand the relationship between all three of those graphs. Expanding this, that's not a 2, that's a equal. Of course, v final minus v initial over t final minus t initial. And what would the graph of this look like? I'm not going to redraw it. Let's go back here and mentally let us change the x to a v. And the average velocity would be the slope of the line connecting v1, v initial, and v final. Same thing, we're essentially just changing the variable. That's nice. You don't have to learn something new for each different one. And of course, yar matey, yar a. Okay, something about this area, right? Okay, I can do it here. Now I can do it. A instantaneous, inst, is written as dv dt. And the same calculus rule applies, and the same graphing strategy applies. Now, what if this change is, what if there is no change? What if the acceleration is constant? What if this equals 0? If that's true, then this is taking us back, those of you who had CAS Avant back in the day, I'm sure you remember the kinematics equations. Equations. Basically, back in the day, you just memorized a few equations. You did not derive those. We are going to know where they came from in this class. That's the difference. One of the differences between AP and honors physics is now we have the math tools, and you guys have the math skills to be at one with these derivations. So, but just to refresh your memory, those equations, one of them was velocity final equals velocity initial plus acceleration times time. Another one was x final minus x initial. We all know this is delta x equals velocity initial times time plus 1/2 a t squared. And there's a third one. I don't know how much you used that back in the day, the good old days. Velocity final squared equals velocity initial squared plus 2 times the acceleration times the displacement. Oh, I used an old word back in the first video. This is displacement, right? Now, I'll be honest with you. You're going to spend most of your time using these as if you've memorized them. Yes, that's true. And you'll have to memorize these equations. You'll use them so much, you probably won't be able to help but memorizing them. But we also are going to spend some time deriving them, and as in the first 2 videos on like completing the square, the derivations include some useful algebraic strategies and tips and tricks and tools that you'll be using many times in solving the problems that you have. So that is where the derivations are useful. You'll never like have on the AP exam derive this kinematics equation. But so in another video I'm going to show you that proof, and the skills you get from that proof will help you solve other problems. Okay, so let's bring this back. Now let's watch what's going on here. I'm going to restart it. First thing I want you to pay attention to is the velocity graph. Watch what's happening to the velocity. Now, you watch the velocity graph. This time, watch the velocity vector, or arrow, on the ball. It's the red one. Ready? Now you should have noticed the following. On the way up, the velocity arrow was pointing up but getting smaller. On the way down, it was pointing down but getting bigger. How does that relate to the graph here? If it's moving up, then its velocity must be up. That's why the arrow was up. And according to this graph, we're calling up positive. So so that's, up here. From 0 all the way up to here is positive numbers. Excuse me. So any part of the graph up here above this axis, this is positive velocity because the values for v are all positive. If you go down here, now v is negative, so the value of v at this point in time, which is 1.5 seconds here, the value for v is negative 5, and that means at 2 seconds, at 1.5 seconds, the ball has a speed of 5 meters per second going down. Right? The thing is, even though the ball is going up and going down, it's changed directions. The slope of the velocity graph is always negative. That may seem strange. You may think, this is positive velocity, this is negative velocity. How come this isn't positive slope? This is a common misconception. This graph, the velocity graph, will tell you the slope of the position graph. If you draw them in this order, displacement, velocity, acceleration, the graph above.
Super ultra great delicious wonderful yabai.
Okay, I didn't mean for you to hear that, but that's my when I plug in a device, that's my sound.
Super ultra great delicious wonderful yabai.
Let's plug that back in. My writing.
Super ultra great delicious wonderful yabai.
My writing tablet became disconnected for some reason. Maybe that's the reason. There we go. For all the crazy writing. Yeah, I got bored with the old doo-doo, doo-doo, doo-doo when you plug in and unplug a USB device. So I picked a little sound bit there. It's embarrassing. Anyway, where was I? Sorry for that distraction. I am not gonna re-record this video. You can pull yourself together. I was saying that the slope of this graph is always described on the graph below it. Let me make that more clear. If you notice, this graph is moving in the positive direction, right? It's moving up. If you were to draw a tangent line, remember I discussed tangent line earlier? If you were to draw a tangent line on this graph, let's say at this point here, the tangent line would look about like that. It would have a positive slope, and if you calculated that slope, it would give you a value of, so if we're looking here, that's at like it's at this time, it would have a value, the slope would be positive 6, 7, 8, positive 8 or so, right? Let me say it one more time, and then I'm going to have to stop the video. If you draw a tangent line here, it's going to have a positive slope, and the slope at this point is determined by rise over run, and the value of that slope is shown on this graph right here at the same time interval, same time position. Alright, that's my time limit.